All right, in this module, we're going to talk about resolution of light microscopes. To start with, a quiz question for you to answer before we proceed is, what do you think the best possible resolution is for a light microscope? So make an educated guess what you think, and we'll come back and talk about resolution. All right, to talk about resolution, we need to look at diffraction. And so we're going to look at diffraction and how it pertains to visible light. So diffraction, as you may know from other classes, is the spreading of light. And this occurs when we have a beam of light and it interacts with an object. So light interacting with an object spreads light. And so to kind of visualize this, I want us to think about a couple of different scenarios where light is traveling through a small opening. So this is sometimes called an aperture, or just an opening or hole, but imagine that this is our aperture, the small opening. And so light is traveling in waves. So these are just kind of meant to represent the wave fronts traveling towards the aperture. When it gets to the aperture, if we have a relatively large size opening, then what we see is the light on the other side is spread a very small amount. So it's basically the same size as over here. So very small spreading that occurs. If we look at a different case where we have a really small aperture, so the opening is very small. So now if we look at those same wavefronts, they encounter this aperture. What happens with this small opening is that we have lots of spreading, right? So essentially what happens is when the light encounters the edge of this aperture, this opening, it appears to bend around the object. So, and it spreads by a given angle. And so the light spread by an angle, and we call this theta. So that's the degree of which it spreads when it encounters this. And so the main takeaway here is that light interacts with these small openings in different ways. Larger opening, not as much spread. Smaller opening, a lot more spread. So that angle theta will increase with the smaller size. And so what's happening here is diffraction. So light diffracts by this aperture, this object, this specimen, and that's what's forming the image, is this diffraction. So diffraction is causing these two scenarios to happen. And the real way that this happens, and how we can explain diffraction, is through the idea of interference. So interference is the recombination or summation of different waves. Recombination and summation of 2 or more superimposed waves. So we're looking at light waves, and we're looking at how they recombined in sum when we have more than 1. And so this is what's responsible for creating the real image that we've talked about so far. So that real image that's produced on the focal plane of the microscope is produced by interference. And so this interference, this combination of waves, can result in 2 different scenarios, and then variations of those 2. We can have constructive interference. This is where the amplitude of the resulting wave is increased. And this happens when we have, for example, if we just have 2, wave A and B, we call them in phase. All right, so that's the first scenario. The second is the opposite, destructive interference. So this is where the amplitude of the resultant wave is increased. Or sorry, this is diminished. So waves that we have, wave A and B, are out of phase. So, like I said, there can be variation between these 2 extremes. For example, in destructive, when they are out of phase by the wavelength lambda, sorry about that. When they are out of phase by the wavelength lambda over 2, then the resultant, let me get that so you can see it, is what we call annihilated. That means it's basically diminished so that we don't have any resulting amplitude. However, there can be cases where we are out of phase by some variation of this, and that just lessens the amplitude. It doesn't completely annihilate that amplitude. All right, so let's take a look at what this looks like when we're looking at these waves. So let me kind of show you examples of this. So for constructive, we'll start with that. Again, we kind of think about A and B. So let's think about an x-axis. We have a sine wave that looks like this, and then another apologize for the drawing, but this is B, and this one down here is A, right? So by saying that they're in phase, what we're saying is the peaks and the valleys, so the maximum and the minimum, line up for A and B. So these are in phase. So the resultant wave, so when these two interact, what they're going to do is they're going to sum. And those two are going to sum such that we have a resultant wave that is the sum of those two waves. So this is the total. That's the resultant wave of those two in phase. So that's constructive. So if we go to destructive, and we look at the conditions there, if we want to look at the case where we have completely out of phase by that lambda over 2, right? So what that means is that, again, I'm going to draw a sine wave. This is wave A. And if they're offset by this lambda over 2, what that means is the second wave is going to look like that. This is going to be B. So it's shifted such that, in this case, the maximum of wave A is on the same x position as the minimum of wave B. So what that does is it annihilates the amplitude of the resultant wave. And so our resultant wave in this case would just be 0. We would, because these are canceling out. They're subtracting. So if one wave was bigger, then the wave amplitude would be minimized, not completely altered. So this is destructive. This is when they're out of phase. So as you can imagine, if it's not this nice lambda over 2, then they can still partially annihilate, but not completely. And so we're going to still have amplitude, but it's just going to be less than what we had with constructive. And so what I want you to think back to now is, in the previous demo, I showed you the laser demo with the meshes. And so see if you can kind of relate what's happening here with interference to what maybe happened with the light waves in the laser pointer when it encountered the object, which is that mesh.